Hi, I'm Mark Stephenson from the APS lab at the University of Colorado Boulder. Today I'll be sharing some work that's being presented at AMOS entitled Safe Autonomous Multi-Agent Inspection of Space Objects Leveraging Relative Orbit Dynamics. So for the problem setting, what is the motivation for autonomous inspection? Well, we know that rendezvous proximity operations and docking missions, as well as in-space assembly and manufacturing missions are becoming increasingly prevalent. So it's important to understand your RSO or resident space object before you do operations, which might be things like preparing for docking, identifying damage, capturing something before deorbiting it, or just characterizing some unfamiliar space asset. One of the big challenges here is the inherent risk present in proximity operations. We don't want to have collisions between our agent and any other satellites in the environment. So briefly, before I go into our approach to the problem, I want to introduce BSKRL, which is a piece of software that the lab has been developing to enable the sort of research that you're going to see here. It combines Basilisk, which is a fast and flexible spacecraft simulation framework, with your standard reinforcement learning interface, Gymnasium, to get BSKRL. So we get all the configurability of Basilisk and the standardized API of Gymnasium. Using the software, we've done research for Earth observation, and as I'll be showing today, this RSO inspection task. I mean, it's completely open source, so I do recommend anyone who's interested in this type of problem to check out this work or my colleague Daniel's presentation later in this conference. So the particular problem that we're looking at here is, given some number of servicers, we want to inspect all illuminated faces of an RSO while minimizing the amount of impulsive thrust we're using. So there's a few specifics that we're going to look at. The control scheme we're using is impulsive burns followed by passive drifts. So we really want to be able to leverage that natural relative motion as much as possible. There's constraints on when we can image a particular part of the RSO based on the illumination coming from the sun, whether it's an eclipse, and what our incidence angle is relative to the RSO and the sun. And finally, we make the assumption that the RSO is nadir pointing in some eccentric low Earth orbit. To formalize this as a Markov decision process, which is necessary to do reinforcement learning, we need to define the different parts of the tuple. So first off, we have our observation space, which includes information about where the satellite is relative to the RSO, where it is in its orbit, how much delta V we've used, when we're going to an eclipse, and most importantly, what fraction of various discrete regions of the RSO have been inspected. In some cases, when we look at training with multiple agents, we're also going to include information about where the other agents are. The action space follows the problem statement. It's a four-element action space. The first three define what thrust we're going to perform up to 1 meter per second. And then the fourth is how long we're going to drift after performing that thrust. Rewards reflect the problem statement as well. We get a incremental reward for inspecting more of the RSO. We get a bonus reward when completing the task. There is, importantly, this negative fuel usage penalty parameterized by alpha, which is going to encourage the agent to use less fuel, especially if alpha is higher. And then we're also going to have a failure penalty of -1 if we enter failure states, such as a collision, using too much delta V, or leaving the region around the RSO. To train these policies, we're using the RL implementation of PPO, which is a state-of-the-art deep reinforcement learning algorithm, and we're training policies over a range of this alpha parameter to see how much control we have over that trade-off between fuel usage and time efficiency. And we train these for 10 to 20 million steps each, which corresponds to a few decades of on-orbit time simulated. Before we can get into the results of the reinforcement learning, we need to look at how we can guarantee safety during execution. We do this using a shield. So the idea behind a shield is we want to interfere with the action that the policy wants to do in order to guarantee it's a safe action. In this case, it looks like an optimization problem. If our policy picks some unsafe action, so one that leads us potentially on an unsafe trajectory, we're going to find the little delta V that minimizes the deviation from the policy's action but guarantees a safe trajectory. Mathematically, this is a pretty standard optimization problem. We have our objective, which is to minimize the deviation from the policy. We're constrained to stay within our impulse limit. We're constrained to not have collisions over some discretized time horizon using the state transition matrix for relative orbits with first orbit eccentricity terms. Finally, we can also use that same first orbit eccentricity assumption to derive some additional constraints that guarantee the secular terms dominate, and that after that explicitly checked for horizon, we're either in a relatively periodic orbit, or we are moving away from the RSO or any other agents. This guarantees safety for the infinite horizon by combining that discrete checkpoints with the long-term constraint. And we know there always will be a solution to this problem because due to the previous iteration of the shield, we're already on a passively safe trajectory, and therefore the trivial solution is to perform no thrust and stay on that passively safe trajectory. Of course, there usually is a better solution than that trivial solution. So let's get into the results for the single agent inspection task. We're going to start on the micro level and look at an individual trajectory. You can see the policy executed for a specific alpha value policy in a fairly high illumination case where most of the RSO is illuminated at some point in the orbit. A large part of the fuel that's used is during that initial large thrust just to get close to the RSO. But after that, it completes pretty sensible inspection trajectory with relatively little fuel. We can then see how the shield works. In this case, we put a very strict version of the shield on the policy, in which case it enforces a 100-meter keep out instead of the 5-meter keep out that the policy learned. We can see that the inspection task is still completed successfully, but the keep out radius is respected over the course of the task. Zooming out a bit, we can benchmark this policy over 1,000 cases. So this is varying what orbit we're in, where the relative initial states are, and as a result of that combination, what parts of the RSO are inspectable over the course of the orbit. The first thing that stands out is that the policy is not, in fact, perfect. It does result in collisions in some cases, which makes sense. It learns that collisions are bad, but there's no mechanism in the unshielded policy to guarantee a lack of collisions. However, with the shield, we can see that that number of collisions has been eliminated and reduced to zero, albeit at the cost of slightly higher inspection durations and delta Vs. We can then zoom out one more step and look at all 7 policies that we trained for different values of that alpha parameter. Each of these clusters is a benchmark over the same 1,000 cases for each alpha value. And we can see pretty quickly that the Pareto front it creates is pretty steep in both directions. That policy we were looking at, the alpha equals 0.2 policy, ends up dominating the vast majority of that trade space. Sure, you can get slightly faster inspection times at the cost of significantly more fuel and vice versa, but overall, there is not a huge amount of ability to select between your inspection time versus the amount of fuel used. Finally, moving on to the multi-agent inspection portion of this. The first attempt in multi-agent inspection was just using that single agent policy, deploying multiple copies of it in the environment and seeing what happens. In order to induce some level of collaboration between the agents, they do share that completion observation. So if one inspects one part of the RSO, it'll tell the other agent that that part of the RSO is inspected, the state is updated accordingly, and the agents should change their behavior based on that. However, we see pretty negative qualitative performance here. The 2 agents end up on very similar trajectories. We're going to be getting pretty similar images of the RSO from both agents. And ultimately, what this shows is the policy has really learned particular trajectories for particular cases. And even if the state is being modified by another agent, it's not a strong enough impact to really diversify the trajectories. However, if we move to learning in a multi-agent environment, so in this case, we have each agent is learning a new policy that takes into account the position of the other agent, we get better results. We see that the trajectories of the two agents are diversified. They're still completing the task in a similar amount of time, but the perspective, the viewing angles that the agents are getting over the course of that inspection task are quite different. We can see this in this animation of that same case. This is a visualization of our physics-based simulation. So up in the upper left there, we get the view of the two inspecting agents, what they are looking at. And on the main screen, the yellow points are points that are currently illuminated by the sun on the RSO. Green points are points that have been inspected by one of the two inspectors with the sufficient illumination levels. You can see as they finish up this last orbit, coming into out of eclipse, those last few points are inspected and the task is completed. So the main takeaways of this work are in the single agent case, we see that the servicers successfully learned to inspect a nadir pointing RSO under these illumination constraints. There's a very steep Pareto front between the usage of fuel and the amount of time used, which really shows limited ability to choose between those two weights. In the multi-agent inspection case, we see that it's important that the agents actively learn how to collaborate with the other agents. This results in diverse inspection trajectories, which is beneficial for the inspection task. However, one result that didn't get to look into depth in this presentation is that with multiple agents, you end up not improving over the single agent case for the amount of fuel used or the amount of time used. It's just too small of an objective. There's not enough work to go around for multiple agents. So future work is going to look at this with larger RSOs where having multiple agents on diverse trajectories is really going to benefit at how quickly you're inspecting the satellite, or in that case, probably something more like a space station or large spaceship. Finally, we demonstrated that our optimization-based shield does work as the math would imply. We eliminate the risk of collisions over thousands and thousands of test cases that are shown in the paper. And even in multi-agent cases where our agents are wanting to go on very similar trajectories, we still see that it performs as expected. Thank you for listening to this presentation. The paper can be found on the website, and feel free to contact me if you have any questions. Thank you.